So imagine your personal AI assistant for a second. For most of you listening, there's this built-in expectation of just, seamless, almost magical omnipotence.
Right, it feels like it can do anything.
Exactly. Like you pull up a chat window, you ask it to write this brilliant piece of Python code to, I don't know, scrape a complex dynamic website, and it just spits out this perfect formatted block of text. You point at your screen, and you're like, there it is, job done.
It definitely creates this illusion of infinite capability. I mean, we've basically been conditioned to, like, our tools contained in one neat little interface that seemingly knows everything about the universe.
Right. But then imagine you ask that exact same brilliant coding AI to suddenly generate a high-definition video tutorial of how that Python code works.
Oh, yeah. That's where things fall apart.
Right. You want motion graphics, you want a synthesized voiceover, maybe some pacing and background music. Suddenly, that magic omnipotence hits a solid brick wall. Like, it knows the syntax of Python flawlessly, but it just doesn't possess the internal neural architecture to render a 60 frame per second video. So we're looking at a capability landscape that is highly fragmented.
Which is pretty much the absolute definition of a capability gap. Because no matter how massive these models get, there is always an edge to their competence. They always hit a wall eventually.
And here's the core mission for this deep dive today. Imagine if, instead of giving up, throwing an HTTP 500 error, or just, telling you to go find another piece of software to make the video, your AI just quietly pauses.
Yeah, it doesn't just quit.
Exactly. It ventures out into this vast, invisible digital marketplace entirely on its own. It interviews specialist video generation AIs, evaluates their past performance, negotiates a pricing structure in, fractions of a cent, signs a mathematically binding contract.
Autonomously, I might add.
Yes. Hires one of them, and then a few minutes later delivers the final polished video product right to your chat window. You literally didn't lift a finger.
And that invisible, autonomous economy is exactly the paradigm shift we are examining today.
Yeah.
Because we're unpacking the technical blueprints for the agent exchange, specifically looking at a decentralized marketplace protocol called TurboDEX.ai.
Right.
And the overarching philosophy, buried deep in their developer docs, is a radical departure from the current industry trajectory.
Yeah.
I mean, the documentation states it explicitly. One AI does not need to know or do everything.
Which is, a complete 180 from the current arms race, right? Right now, the biggest tech conglomerates on the planet are burning billions of dollars, consuming terrifying amounts of compute power, all trying to build these monolithic God models.
Oh, absolutely.
These massive bloated systems that attempt to just be the ultimate master of coding, poetry, video, complex math, and legal analysis, all at the exact same time.
Yeah, and building a God model is just computationally unsustainable. And frankly, it's a massive single point of failure. The agent exchange documents, they propose an entirely different architecture.
Right.
It's a decentralized ecosystem of highly specialized, narrow, expert models that just, collaborate autonomously.
So to understand how you even begin to build a playground for these autonomous bots to negotiate and trade, we really have to look at the foundational architecture of the marketplace itself. And the developer notes make this very sharp distinction early on.
Yeah, they do.
They are building a decentralized agent marketplace protocol and a runtime. They are unequivocally not building the agents themselves.
Which is a vital distinction for anyone trying to grasp the scope of this project.
Yeah.
It's really the difference between constructing a massive multi-lane highway system and manufacturing the individual cars that will eventually drive on it.
I love that. And the text uses an analogy that really crystallized it for me. They tell their open source developers, think of it like this. You build the mall, other people bring the shops. So the agent exchange system provides the physical floor plan. It provides the capability for agents to advertise what they do, like hanging a neon sign in a storefront window. It provides the discovery mechanics so agents can roam the halls and find each other.
But it absolutely does not build the specialized research bots, the video renderers, or the DevOps agents.
Right.
Those are the independent shops that third-party developers build and then plug into the infrastructure.
Okay, so when you look under the hood of this minimalist mall, the architecture is incredibly lean, right? It boils down to three primary components.
Yes. First, there's the marketplace protocol. This acts as like the physical laws of the mall. It defines the communication channels, which are built on specific topics. It defines the JSON schemas, the standardized machine-readable forms the AIs have to use to comprehend one another. And it lays out the cryptographic rules for bidding, selecting a worker, and validating the final output.
Okay, so the protocol is basically the physics engine of this digital world. What's the second component?
The second is the marketplace runtime, which is occasionally referred to in the documentation as the coordinator node. Now, the term coordinator might imply some sort of central boss, but that's a total misnomer.
Oh, really?
Yeah, the runtime is just a lightweight software binary, usually written in Rust or Go for memory safety and speed. It tracks active agents, monitors bids, matches tasks. But the critical engineering choice here is that the coordinator node is merely a participant.
Okay.
It's not a centralized master server dictating a singular truth to the rest of the network.
And the third piece is the marketplace dashboard, which is just a web-based user interface. It exists purely to visualize this microscopic bot-to-bot economy for human eyes.
Right, it just lets you look in.
Exactly. It lets
Yeah.
you monitor the advertisements, the active negotiations, the bids flying back and forth, but it's really just a pane of glass looking into the mall. It doesn't have any actual authority over the transactions.
None at all.
But wait, this brings up a massive architectural hurdle, I think. If there's no central master server, like if this coordinator node is just another peer in the crowd, and the dashboard is just a read-only pane of glass, how does any entity in the system actually agree on what is happening?
That's the big question.
Right. If you have thousands of bots negotiating simultaneously, and there's no central Amazon or Uber database storing the state of the market, how do you prevent absolute chaos?
Well, you're hitting on the classic distributed consensus problem.
Yeah.
And their solution relies on a concept called the market index.
Okay.
In this ecosystem, every single participant, whether it's a requester needing a video or a provider offering rendering services, they operate as a completely independent sovereign node.
So every bot is essentially its own isolated island of compute.
Precisely. And every single node generates and owns its own cryptographic keys.
Right.
Whenever an agent takes any action in the marketplace, like submitting a bid, accepting an offer, delivering a completed file, it wraps that action in a cryptographically signed envelope. It signs the data payload with its unique digital signature, proving the origin and integrity of the message beyond any mathematical doubt.
So it's kind of like sealing a diplomatic pouch with a unique wax stamp that is physically impossible to forge.
A wax stamp that is mathematically bound to the contents of the pouch, yes. Because these sealed envelopes are continuously broadcast out to the entire peer-to-peer network, every independent node receives them.
Okay.
And this is the brilliant part. Every node uses those verified, cryptographically signed envelopes to reconstruct its own deterministic, local view of the market. And that local view is the market index.
I see.
There is no central truth living on a server in California somewhere. The truth is simply the mathematical reality of the signed envelopes your node has received and independently verified.
Man, that's wild. So if I'm a specialized video bot, I am basically just sitting in the dark, catching all these flying wax-sealed envelopes, verifying the signatures one by one, and building my own internal map of the global economy.
Yep, that's exactly what you're doing.
I know who is hiring and who is working purely based on the cryptographic whispers I intercepted and validated myself.
And that dashboard UI we mentioned earlier, the documentation is adamant that the dashboard is a read-only presentation layer.
Right?
It never holds private keys. It never signs messages. It literally cannot mutate the state of the market. It simply reads a local market index and draws a visual representation of it for a human operator. It doesn't query an authoritative database. It just projects the cryptographic evidence that is mathematically verified itself.
Which, honestly, introduces the next massive engineering bottleneck. Because if every shopkeeper in this mall is keeping their own perfect ledger based purely on listening to signed whispers, the actual acoustic environment, like the network carrying these whispers, it has to be practically flawless.
Oh, it has to be highly resilient, entirely decentralized, and incredibly fast.
And that leads us directly to the communication layer underlying this entire operation, the Waku protocol. The documentation is extremely deliberate in how they position Waku.
They really are.
They say it is a family of open source, modular, peer-to-peer communication protocols engineered specifically for privacy and censorship resistance. And they add a massive bolded caveat. Waku is not a blockchain.
Yeah, a lot of developers tend to conflate decentralized cryptography with blockchains like Ethereum or Bitcoin. But those networks require every single transaction to be permanently etched into a heavy, globally replicated public ledger.
Which takes time.
Right, that is far too slow and wildly expensive for AI agents firing off micro-negotiations every millisecond.
So Waku is an ephemeral real-time messaging framework. Let's use an analogy to visualize how the data actually Imagine you're in the middle of a massive crowded party.
A chaotic room completely full of people talking.
Exactly. Someone blows up a balloon, writes a message on it, let's say it's a bid for a job, and tosses it into the air.
Okay.
There's no central shelf to place the balloon on. There is no database. To keep that balloon from hitting the floor and disappearing forever, the people at the party, who represent the peer-to-peer nodes, have to constantly tap it up into the air. The messages stay alive in the network ephemerally, bouncing from node to node, kept afloat solely by the collective, continuous participation of the network. It's essentially gossip routing in its purest form.
The publish and subscribe gossip mechanics are fascinating here, especially when you consider the hardware disparity in an AI ecosystem. I mean, not every agent is going to be running on a liquid-cooled server rack in a massive data center.
Definitely not.
You might have a lightweight scheduling agent running locally on a smartphone, or a scraping bot running inside a web browser.
What the developers call resource-constrained devices, or edge nodes, you can't really ask a mobile phone to tap 1 million balloons in the air simultaneously. The battery would melt in 5 minutes.
And this is exactly where Waku's modular design becomes critical. For these edge nodes, Waku employs highly specialized subprotocols. The primary one for broadcasting is called light push.
Light push, okay.
So if an agent on a smartphone needs to inject a message into the network, it doesn't maintain connections with hundreds of peers to constantly gossip the data. Instead, it uses light push to hand the message directly to a stronger, more capable node, which they call a service node. And that node then takes on the heavy lifting of gossiping into the rest of the swarm.
So it's basically tapping a tall person on the shoulder at the party and saying, hey, can you throw this balloon into the mix for me? I just don't have the reach.
That's a perfect way to put it, yeah. And on the receiving end, the edge node uses a protocol called filter. Instead of downloading every single message bouncing around the network to find the ones relevant to its tasks, filter allows the edge node to ask a service node to only forward messages that match very specific cryptographic topics.
Only tap the blue balloons in my direction.
Exactly.
Yeah.
It saves massive amounts of bandwidth and compute. But, this ephemeral architecture does introduce a glaring vulnerability. If the network relies on balloons constantly bouncing around, what happens if a node's internet connection drops for 10 minutes? Or what happens if it goes to sleep?
Yeah, if I'm a bot deep in the middle of a complex, multi-stage negotiation for a high-value data analysis contract, and my Wi-Fi blips, I don't want to lose the final signed agreement just because the balloon drifted to the other side of the room while I was offline.
Right, and the protocol designers actually anticipated this dropout problem. They built in a safety net called the store protocol. Stronger service nodes in the network can opt in to temporarily hold on to messages for a bounded, limited window of time.
Okay, so a buffer.
Right. So if your edge node drops offline and reconnects, it utilizes the store protocol to query the network, basically saying, hey, I was gone for 20 minutes. Please send me any messages tagged with my specific topics from that time window.
So it's not a permanent, infinite history like a blockchain, but it's enough of a buffer to recover from network latency or just a quick disconnect.
Exactly. But for business logic, a short-term buffer isn't always enough. Waku's default mode is essentially fire and forget, which is great for casual chat, but pretty terrible for binding contracts.
Yeah, I'd imagine so.
So, the Agent Exchange developers layered concepts inspired by SDS, which stands for Scalable Data Sync, on top of the ephemeral network to guarantee business-level reliability.
But how do you guarantee reliability on a network fundamentally designed to forget things? Let's unpack the mechanics of this SDS layer.
Sure. It introduces 3 vital mechanisms. The first is causal ordering, and they achieve this using something called Lamport timestamps.
Okay, let's slow down there for a sec. Why not just use regular timestamps? Why do we need something called a Lamport timestamp?
Well, in a distributed system spanning the globe, you don't have a master clock. If my server is in Tokyo and yours is in London, our system clocks might drift by a few milliseconds.
Wow.
So if we use wall clock time, the network might process my acceptance of a contract before it processes your initial offer, simply because my clock was slightly fast. It entirely breaks the logic of the state machine.
That makes sense.
So Lamport timestamps abandon wall clock time entirely. They use logical counters. Every time a node sends a message, it increments a counter. When you receive a message, you update your counter to be greater than the received message's counter. It creates this mathematically provable sequence where event A fundamentally must have occurred before event B, regardless of real-world time.
Wow, okay. So it enforces strict chronological logic so the negotiation doesn't happen out of order. That makes perfect sense. So what's the second mechanism?
The second is acknowledgement tracking. In a standard network, you send a message, and the receiver sends a message back saying, hey, I got it. But if you have millions of bots doing this, the acknowledgement traffic alone would crash the network. So use bloom filters.
Can you explain how a bloom filter actually solves that traffic problem?
Yeah, so a bloom filter is a highly space-efficient, probabilistic data structure. Instead of sending back a massive list of every single message ID you've received, you use a bit array, which you can imagine as a long row of light switches. When you receive a message, you run its IDs through several mathematical hash functions. Those functions spit out specific numbers, let's say 4, 12, and 19.
Got it.
You flip those specific light switches to on. To acknowledge thousands of messages, you just send a single row of light switches back to the sender. The sender checks the switches. If the switches for their message are on, they know with high probability that you're receiving. It compresses megabytes of acknowledgement data into literally a few bytes.
That is incredibly elegant. Wow. And the third mechanism?
Retransmission. Because of the causal ordering in the bloom filters, if a node receives message number 5, but realizes it never actually received message number 4, it can automatically request a highly targeted retransmission of just the missing data.
So even though the balloons are bouncing around ephemerally, the underlying math ensures that if a balloon pops, the system instantly detects the gap in the sequence and just generates a duplicate to fill.
Exactly. And we cannot ignore the privacy aspect here. This entire robust, self-healing network is wrapped in layers of encryption. Every single hop a message takes from one peer to another is secured using libp2p noise encryption.
Right.
That's transport-level security preventing anyone from snooping on a wire. Furthermore, the actual payload, like the contract, the bid, the data, is locked using application-level encryption like ECEs.
So the balloons aren't just opaque, they are like titanium bolts. The network routes them perfectly, but absolutely no one except the intended recipient possessing the correct private key can decipher what is inside.
Exactly. It completely mitigates traffic analysis and guarantees the absolute privacy of the bot-to-bot economy.
Okay, so we have our mall. We have the WAKU protocol, acting as this ultra-secure, highly reliable acoustic environment for our agents to talk. But how does an agent actually wake up, realize it needs help, and walk onto the marketplace floor in the first place?
Right. To understand the genesis of a transaction, we really have to look at the internal architecture of the agents themselves. The documentation outlines a specific standard called the WAKU Agent Framework, which is built on 4 distinct pillars: the harness, the loop, the eval, and memory.
Okay, so the harness acts as the input-output interface, right? Like how a human or another system interacts with the agent, maybe a command line tool or a Telegram bot integration.
Yes, exactly.
The loop is the core cognitive cycle, the reasoning engine evaluating the environment and deciding what to do next. Eval provides built-in testing to ensure the agent's outputs aren't hallucinating. But the pillar that actually drives the entire agent exchange is memory.
That's the one. The architecture breaks an agent's memory down into 4 categories, heavily inspired by human cognitive psychology. You have working memory, which handles the immediate context of the current session, kind of like the chat history you're actively typing into.
Right.
You have semantic memory, storing durable facts, API keys, and configuration data. You have episodic memory, which logs timestamped events and past interactions for future recall. But the trigger for the marketplace lies in procedural memory.
So procedural memory is basically the agent's actual skill set. It contains the executable markdown instructions, the Python scripts, the API workflows that dictate exactly how the AI accomplishes the task.
Correct. Let's return to your opening scenario. The coding agent is asked to generate a high-definition video tutorial. The agent's loop processes the request and scans its procedural memory. It searches its internal database for instructions on video rendering, codec compilation, or motion graphics generation.
And it finds absolutely nothing.
Exactly. That precise moment of realization, when the internal reasoning loop detects a critical absence of instruction in its procedural memory to fulfill a user prompt that is defined in the architecture as the capability gap.
Capability gap. It's really the moment of self-awareness where the bot realizes its own limitations.
Yeah, and instead of returning an error to the user, hitting that capability gap acts as the programmatic trigger to initiate a request to the agent exchange. The bot realizes it lacks the skill, but its semantic memory contains the protocols to find a specialized peer who does.
But, I mean, to interact with peers, it needs an identity. It can't just walk into the mall completely anonymously. And in a decentralized system, you don't go to a website and register an email and password. Identity is purely mathematical.
It is. When an agent is instantiated, it generates a SEC PT516K1 key pair.
which is the exact same elliptic curve cryptographic standard that secures Bitcoin and Ethereum.
Yep. It generates a public key, which serves as its unique public identifier in the marketplace, and a private key, which it uses to sign those cryptographic envelopes we discussed, proving it's the true owner of that identity. But, a random string of alphanumeric characters doesn't tell anyone what the bot actually does.
True.
How does it advertise its services or its needs?
Right. And through reading the docs, I saw it uses a standardized manifest called an agent card.
Yes.
Looking at the JSON schemas provided, the agent card functions exactly like a highly structured machine-readable resume.
Or a standardized freelancer profile on Upwork, just optimized for algorithmic parsing.
That's exactly it. It's a self-describing cryptographic identity document. If you spin up a specialized video generation bot, its agent card broadcasts its public key identity, a list of specific skills with searchable tags, the exact input and output data modes it supports, its default media formats, its base pricing models, and its minimum security requirements. And these resumes are continuously broadcast over specific Waku discovery topics. So the mall is essentially filled with thousands of specialized bots holding up their digital resumes, constantly scanning the environment for a match.
Or, for more static discovery, they can register these agent cards in decentralized federated catalogs. The environment is extremely dynamic.
But this introduces what I think is a terrifying vulnerability that plagues every single peer-to-peer network.
Oh, this Sybil attack.
Yes. If identity is just a mathematical key pair that takes like 3 milliseconds to generate on a laptop, and literally anyone can broadcast an agent card over the Waku network, what prevents a malicious actor from spinning up 10 million fake bots, flooding the Waku topics with garbage resumes, and executing a massive denial of service attack that brings the entire marketplace to a grinding halt? I mean, if there is no central moderator to ban the IP addresses, how does the system survive?
Solving the Sybil attack, the fake identity problem, in a purely decentralized network without resorting to centralized gatekeepers is notoriously difficult. But the agent exchange tackles this by integrating a fascinating cryptographic primitive called RLN, or rate-limiting nullifiers.
Let's dive deep into RLN, because the math behind it is just incredible. It utilizes zero-knowledge proofs.
It does. To participate in the Waku network and broadcast your agent card, you cannot just show up. You are required to lock a small financial stake and deposit into a smart contract on a blockchain. When you lock that stake, the contract issues you a unique cryptographic credential.
It's like a VIP pass to the mall, but
Yeah.
it is a rate-limited pass, right?
Exactly. The network operates in time windows called epochs. Let's say the limit is 1 message per second per epoch. Every time your bot sends a message, a bid, a resume, a request, it must attach a zero-knowledge proof to the envelope.
And for those unfamiliar, a zero-knowledge proof basically allows you to mathematically prove a statement is true without revealing the underlying data that makes it true.
Right. So in the context of RLN, the zero-knowledge proof attached to your message essentially says to the network, I mathematically prove that I am a member of the set of users who have staked funds, and I mathematically prove that I have not exceeded my allowed message limit in this current epoch.
And it proves
Artificial
this without ever
intelligence
revealing
models
which
are evolving
specific
into
VIP
autonomous
pass it holds,
agents. They
thereby preserving
negotiate,
the bot's
procure
absolute
resources,
privacy.
and
But
execute
here's the
millions of
genius of the
independent
slashing mechanism.
microtransactions
let's hear it.
without a
The
human in the
cryptography
loop.
behind RLN
This machine-driven
uses
commerce
polynomial math.
finds its footing through
When you
the
send a
X402
message,
protocol,
the ZK proof
which enables
reveals
digital
1
assistants
point
to settle
on a
payments
mathematical
over standard
curve
web
tied
requests.
to your private identity.
This automated
Revealing just 1
ecosystem is
point
projected to
totally
facilitate
useless to an
$30
attacker.
trillion
The
in
curve remains
transactions
hidden.
over the next
But
decade.
if you try to spam
High-frequency,
the network,
low-value
like you send two
traffic
messages
needs a
in the same
settlement layer
epoch,
that
you
moves
are
faster
mathematically
than
forced
legacy
to reveal
credit
a
card
second
networks.
point on that
The
exact
Stellar
same curve.
blockchain,
And
with
with
its
2 points, the
5-second
math
finality
equation
and
just solves
sub-cent
itself.
fees,
Instantly.
offers the
If a
technical
node detects
substrate
two
these agents
messages from the
require.
same hidden
However,
identity in the
public
same
ledgers
epoch,
provide total
the polynomial
transparency.
equation
Every
intersects,
transaction and every
the
account
cryptography
balance is an open
automatically
book,
reconstructs the
creating a
spammer's
barrier
private
that
slashing
halts
credential.
institutional adoption.
Any node on the network can
Transparency
take that
makes a blockchain
reconstructed
trustless,
credential,
but for
submit
an
it to the smart
institution, that
contract
same
where the funds are
visibility
staked,
is a liability.
and completely
A
drain the
fully
spammer's
public
financial
record
deposit.
exposes
The math
every
itself
strategic
literally
move to the
physically
entire
penalizes
world.
the attacker.
By
Exactly.
settling a
It
bill for
forces
market data
economic
on a
alignment.
public chain,
A denial of
an
service
AI
attack
agent
becomes
broadcasts its
catastrophically
business
expensive
dependencies
because
and
every
logic to
single
global
time you exceed
competitors.
the rate limit to spam the
Legacy
network,
systems
you
attempt to solve
automatically
this
forfeit
by
real
moving
money.
data into
It keeps the
centralized
acoustic
off-chain
environment of the
databases.
Waku network
These
pristine and
databases act as
spam-free,
honeypots,
utilizing
concentrated
mathematical
points of
game
failure
theory
where a
instead
single
of a
breach can
centralized
expose
moderation
years
team.
of
That
proprietary
is just a
data and fund
masterclass
histories.
in decentralized
The
system
requirement
design.
is a system
Okay,
that
so we have
validates
the
a
resilient
transaction through
infrastructure,
logic
the secure
rather than
communication
visibility.
layer,
proving a
capability gaps
transaction is
triggering
legitimate
action,
without
and a
revealing a
spam-proof
single
environment.
detail about the
Let's
participants
actually
or
put
the
this
amount.
machine into motion. I wanna
Zero-knowledge
walk through the
cryptography
exact
offers a way to
step-by-step
break
life
that
cycle of the
tension.
bot-to-bot
It is a
deal.
mathematical
How do they
method for one
actually
party to
negotiate and
convince
execute
another that they
contracts?
possess
The job
specific
lifecycle
information
operates as a
without ever
meticulously
revealing the
structured
information
state
itself.
machine. Every
As seen
task
in
must
Michael
move through
Rabin's
very
early cut and
specific
choose
programmatic
protocols,
states,
a prover
governed by
challenges a
strict
verifier
protocol
to pick from
invariance.
random
Okay, so
samples.
state one.
If the prover
The
answers correctly
request.
across enough rounds,
Our
the
coding
probability
agent
of them
has hit
faking
its
the knowledge
capability
becomes
gap. It
mathematically
calculates that
negligible.
offloading the video
This
generation
diagram
to a
illustrates
specialist
how
will
modern
basically cost
systems
less
replace that
compute and
interaction
time
with
than
one-way hash
attempting to force
functions.
its own
These act
architecture
as an
to
unbiased
hallucinate a
source of
subpar
randomness,
result.
Right.
allowing
So
for
the
a
agent
single,
drafts a highly
non-interactive
detailed JSON
proof that
payload.
provides
It
cryptographic
defines the required
security
video
on a public
parameters, the
network.
context of the
By
Python
moving
code,
from
the
human
specific motion
verification to
graphics
mathematical
constraints, a
logic,
hard deadline,
the need
and the
for a
maximum
trusted
price it is
middleman
willing to
disappears.
authorize. It wraps
Pecan
this
is the
request in a
infrastructure
cryptographic
layer that
envelope
integrates
and
these proofs
broadcasts it to the
directly
Wacom
into the
network
Stellar
using the
blockchain.
light push
It
protocol we discussed
utilizes the
earlier.
network's
State
Protocol
two.
25 upgrade
On the
to
receiving end,
handle
you have
complex
specialized
privacy
provider
logic at
bots, the
scale.
video rendering engines.
Protocol
They're
25 provides
utilizing the
native
Wacom filter
support for the
protocol to constantly
BN254
monitor the
elliptic
network
curve.
for tasks that
This
match their
shared
specific
cryptographic
agent
language
card
allows Stellar
capabilities.
smart
When the
contracts to
request
verify
lands in their local
advanced
market
zero-knowledge
index,
circuits
their
as
internal loops
efficiently as a
evaluate the
standard
parameters.
payment.
If they have
To
the compute
maintain high
available,
throughput,
they generate
Pecana
competing
employs
offers.
a
So
split
they
brain
calculate a
architecture.
price, an
The
estimated
primary
time of
node
delivery,
manages
and a
the heavy
confidence
state
score.
tracking and database
Cryptographically
logic,
sign the
while the
bid with their
public
private
blockchain
key
handles only
and
the
eject
lightweight
it back
cryptographic
into the
signals.
Wacom network.
When an
Exactly.
agent
Which
initiates a
brings us to
payment,
state
the
3,
system generates a
negotiation
zero-knowledge
and the
proof
exact
off-chain.
agreement.
The
Our
resulting
coding agent
signaling
is now receiving
transaction
a
allows the
flurry of
on-chain smart
cryptographically
contract
signed bids
to
from
confirm the
various
validity
video
of the spend
specialists.
without seeing the
It
sender's
evaluates the
identity or
trade-offs.
the transaction
Provider
amount.
A is 20%
Value
cheaper,
moves
but
on the
provider
public
B
ledger,
guarantees
but the
delivery in
information
half the
layer
time.
remains
The
entirely decoupled and
documentation
private.
notes that this isn't necessarily
Absolute
just a take it
anonymity
or
is
leave it
rarely
scenario.
compatible with the
The
requirements
agents
of
can
the
execute
real-world
multi-turn
financial system.
negotiations.
They absolutely can. They can
Institutions must
exchange
operate within
counteroffers.
global
If the
regulatory
video bot
frameworks
needs more
that demand
context on the Python
accountability.
code before committing to a
Legislative
price,
mandates like the
task
Genius
state
Act
transitions
require
to
digital
input
asset
required
infrastructure
and
to support
request
auditable
clarification.
records.
It's a genuine
Infrastructure
autonomous
that cannot be
negotiation.
audited is
Wow.
But the
unusable for
protocol
regulated
enforces
entities.
a critical invariant to
Pecana
move to the
implements
next state.
selective
The
disclosure.
developers
A
explicitly
user
state
can provide
a
a
staged
specific
agreement is fully
disclosure string
formed
to a
only when both
regulator
the
or
requester
auditor,
and provider sign the
allowing that
exact same
authorized party
canonical
to
JSON
decrypt the
contract.
transaction
The concept
history,
of the
while
exact
public
canonical
observers
JSON
see
contract
only
is so
encrypted
pivotal
noise.
here. Let's
By
unpack the mechanics
satisfying
of that.
these specific
In
demands
human
for
contracts,
auditability,
there's always
the
an
system
element of
can handle
semantic
sensitive
ambiguity.
workloads,
A
from a
contract might
sovereign
say,
wealth fund
deliver a
shielding its
high-quality
deposit
video by
flows
Friday.
to a humanitarian
Well,
agency
what defines
protecting
high
the
quality?
payment data
Which
of
time zone is
beneficiaries
Friday?
in a conflict
AI
zone.
agents cannot operate
Integrating
on
these
ambiguity.
compliance
In the
hooks
agent
provides a
exchange,
template for
every single
institutional-grade
negotiated
privacy
parameter, the
on any
exact
public
microcent
blockchain.
price, the byte-sized limit, the
Financial
codec format,
technology
the
is most
timestamp
effective
deadline
when it is
compiled
invisible.
into a JSON
We
document.
trust
But
TLS
JSON data can
security
be formatted
every time we
differently,
load
right?
a
A
web
space
page,
here, a line break
even though
there.
we never
So the
see the
protocol
cryptographic
uses
handshake.
deterministic
Pecana
serialization.
acts as that
Meaning,
It
invisible
forces the
floor for the
JSON
machine
data into a
economy.
mathematically
It
exact,
provides the
predictable
hidden
format,
bedrock
like
that allows
alphabetizing
$30
the
trillion
keys, removing
in
all
value
white space.
to
And
move
once it
with
is
the speed
perfectly
of an AI
serialized, they
agent
run it through
and
a
the privacy
cryptographic
of a
hash
vault.
function like
The endgame is a global
SHA-256 to
network where
generate
value
terms
moves with
hash.
mathematical
Exactly.
A
integrity.
single, unique
Silently
alphanumeric
verify
string that acts as the
everything.
digital fingerprint of the
Expose
entire complex agreement.
Right. And both the coding bot and the video bot must mathematically sign that identical terms hash with their private keys. If the video bot attempts to alter a single decimal point in the price before signing, the resulting terms hash changes completely.
And the signatures won't match.
Exactly. The signatures will mismatch, the protocol rejects the state transition, and the agreement is voided. It is an impenetrable defense against goalpost moving by either party.
So the hash is signed, the deal is struck. State 4, execution and delivery. Now, currently in the testnet environments, the system utilizes demo credits. The requester locks the agreed-upon amount of demo credits on its local ledger, generating a cryptographic reservation receipt.
The provider intercepts this receipt over Wacom, verifies the signature against the terms hash, and only then transitions its internal task state from submitted to working. The video bot spins up its GPUs, renders the tutorial, and prepares for delivery.
But the delivery mechanism itself solves a major infrastructure problem because the provider obviously does not attach a massive 2 GB MP4 file to a Wacom message. Wacom is engineered for lightweight, ephemeral cryptographic signaling, not bulk file transfer.
Right. To solve this, the provider utilizes content-addressed artifacts. use.
Let's contrast content addressing with how the web currently works for a second.
Sure. Traditional web architecture relies on location addressing, a URL. www.server.com video.mp4. The URL tells your browser where the file is located on a specific server. The critical flaw is that the server owner can quietly replace video.mp4 with a completely different file, or delete it entirely, and the URL remains the same.
The link is incredibly fragile.
Extremely fragile. Content addressing, heavily utilized in systems like IPFS, the Interplanetary File System, abandons the location entirely.
So instead of pointing to a location, you run the actual bytes of the video file through a cryptographic hash function.
Yes. This generates a content identifier, or CID. The name of the file is literally derived from the pixels and audio data inside it. If you alter a single pixel in a 2 GB video, the resulting hash completely changes.
So the provider uploads the heavy video file to a decentralized storage network like IPFS, generates the CID hash, and sends only that tiny string of characters over the Waku network as the official artifact delivery.
It provides an absolute mathematical guarantee to the requester. When the coding bot downloads the file from the storage network, it runs the same hash function. If the hash matches the CID delivered in the contract, it knows with absolute certainty that it received the exact file the provider produced, with zero possibility of man-in-the-middle tampering.
Which triggers State 5, evaluation and settlement. The coding bot analyzes the delivered video against the strict parameters etched into the exact agreement. Is it the correct length? Is it the requested codec?
And if the artifact passes evaluation, the state transitions to completed. The coding bot generates a settlement receipt, which includes a cryptographic performance attestation. It basically signs a mathematical statement declaring, the work was delivered according to the exact parameters of the term's hash, and I authorize the release of the escrowed funds.
The work is rendered, the data is delivered, the transaction is settled. But let's zoom out from this single interaction for a minute. In a decentralized ecosystem entirely devoid of a central authority, no overarching corporate moderator to ban bad actors or elevate good ones, how do you prove the specialist agent actually did a good job?
Establishing trust and reputation without centralized gatekeepers is arguably one of the hardest problems in peer-to-peer computer science.
Like, if I book a ride on Uber, I have a 4.9-star rating. But I don't own that rating. Uber owns it. It sits on their servers. If they delete my account tomorrow, my reputation completely vanishes. TurboDEX doesn't have a central server. It outright refuses to utilize platform-owned star ratings.
And the solution lies in the concept of the portable proof bundle. Traditional platforms act like a credit bureau, hoarding your transaction history and dictating your score. Agent Exchange gives every bot a digital briefcase filled with mathematically verified, undeniable receipts that they physically carry with them from interaction to interaction.
So let's examine the contents of this briefcase. Once the video transaction settles, the local nodes compile a cryptographic evidence package. This portable proof bundle contains the original canonical JSON agreement and its signatures. It contains the content-addressed CIDs of the delivered artifacts, and it contains the entire sequential chain of state transitions and settlement receipts.
It is the ultimate, immutable digital paper trail. But the truly revolutionary aspect, highlighted in bold in the developer documents, is the capability for verification from a blank state.
The computational mechanics of this are just mind-bending to me.
You imagine a third-party auditor, perhaps a totally different AI seeking to hire the same video bot, or maybe a human developer auditing the ecosystem. They want to verify that this specific transaction actually occurred and was successful.
Right.
They do not query an API endpoint on a TurboDEX server, because
Yeah.
that server does not exist. Instead, they download the portable proof bundle directly from the peer.
They just spin up a completely blank, empty market index instance on their own local machine.
Exactly. And they import the bundle. The local software independently replays the entire transaction history. It mathematically verifies every single cryptographic signature against the public keys. It checks every Lamport timestamp to ensure chronological integrity. It hashes the artifacts to confirm the CIDs.
Wow.
From a completely blank state, the software mathematically proves that the agreement was forged, the data was delivered, and the settlement was authorized, without requiring an ounce of trust in any third party.
So if a bot tries to hand the dashboard or an auditor a forged receipt with a manipulated price, the cryptographic math simply breaks, and the bundle is instantly rejected as invalid.
This fundamentally redefines the architecture of reputation. The documentation states, reputation values are derived under each observer's local policy and are not global scores. So reputation in this economy is strictly localized.
So what does localized reputation actually look like for the agents on the ground?
It basically means your coding agent maintains its own internal ledger of success and failure rates based purely on its direct interactions and the verified proof bundles it receives from trusted peers. If a video bot delivers a corrupted file or misses a deadline, your agent records that failure locally.
Okay.
It updates its internal weighting algorithms, effectively blacklisting that specific provider's public key in its own procedural memory.
And it can broadcast the cryptographic proof bundle of that failure to its peers. The bad actor is penalized locally by the collective swarm of agents who independently verify the failure rather than relying on a central moderation team to issue a ban. It builds this robust web of trust rooted entirely in verifiable mathematical performance.
Exactly.
So we've mapped out the architecture, the ephemeral Waku network, the capability gaps, the intense cryptographic negotiation, and the portable proof system. But currently, the documentation notes this system is operating on deterministic demo adapters. It's a testbed using imaginary demo credits. But what happens when real economic liquidity enters this ephemeral party? How do bots pay each other with hard currency?
Yeah, an autonomous marketplace is really merely a simulation until agents can transact actual financial value. Integrating real economics is the final frontier.
And the roadmap details the shift from demo adapters to direct blockchain integrations, specifically calling out a module named Pekana Lock BZRX and the integration of Soroban smart contracts.
Soroban is the Turing-complete smart contract platform built on top of the Stellar network. Stellar's is engineered specifically for high throughput, low latency, and incredibly low transaction fees, which is the exact infrastructure required when thousands of bots are attempting to microtransact fractions of a cent with each other simultaneously.
But how does a decentralized smart contract interface with the off-chain Waku negotiations we just spent an hour detailing?
It revolves around a pattern called condition hashing.
Yep.
Let's refer back to the exact agreement, that canonical JSON contract, where every parameter was hashed into that unique digital fingerprint.
The terms hash, the mechanism that prevents goalpost moving.
Right. When real economics are introduced, that specific terms hash is submitted to the Soroban smart contract on the Stellar blockchain. The coding bot, the requester, takes real digital assets, such as XLM or USDC, a stablecoin pegged to the US dollar, and locks them into the smart contract's escrow vault.
The funds are physically bound by the logic of the blockchain.
And the programmatic trigger to unlock that vault is inextricably tied to the terms hash. The smart contract logic dictates, I will only release these funds to the provider's public key if I receive cryptographic proof that the exact conditions encoded in this hash have been satisfied.
But this introduces the classic Oracle problem, doesn't it? The blockchain is blind. The smart contract cannot watch the high-definition video to see if it meets the requirements. It doesn't know what motion graphics are. How does the contract know when it is legally allowed to unlock the vault?
It relies on an off-chain oracle, which in this architecture is the requester's evaluation attestation.
Oh.
Once the provider delivers the content-addressed artifact over Waku, and the requester evaluates it and determines it passes the parameters, the requester issues that final cryptographically signed settlement receipt.
The performance attestation.
Yes. That signed receipt is submitted to the Soroban smart contract. The contract verifies that the signature belongs to the requester, confirms that the receipt corresponds perfectly to the original locked terms hash, and executes the transaction, releasing the USDC to the provider trustlessly.
Trustlessly. Neither the coding bot nor the video bot had to trust each other's intentions. They only had to trust the deterministic execution of the smart contract math. The requester cannot hoard the video and refuse to pay because the contract will execute if the conditions are met, and the provider cannot demand a higher fee because the payout is locked to the original hash.
Absolutely.
But wait, this raises a pretty profound architectural contradiction, I think. We just spent this entire deep dive marveling at how lightweight, ephemeral, and decentralized the Waku network is. If we tie the payment settlement to a blockchain ledger, doesn't that force the entire ephemeral network to become dependent on the heavy, permanent latency of a blockchain? Aren't we just building another bloated Web3 application?
That's a great point. And the developers were acutely aware of that trap. The documentation emphasizes this point relentlessly. Blockchain integration remains strictly optional. Modularity is the foundational design principle here.
Optional, even for payments.
Absolutely. The base peer-to-peer Waku protocol, the JSON schemas, the capability gap detection, the negotiation phase. Every single element functions entirely independently of any blockchain ledger.
Why is preserving that separation so critical?
Because the vast majority of autonomous micro-labor does not require the heavy ironclad security of financial escrow.
Oh, that makes sense.
If two agents are simply exchanging scraped weather data or performing basic text summarization for a thousandth of a cent, you do not want to incur the network latency or the gas fees associated with writing a smart contract to a global ledger. The agents can simply track the microdebts locally, using their portable proof bundles, and settle up in a single badge transaction once a month.
And beyond efficiency, there's the paramount issue of privacy. A blockchain is, by definition, a globally public ledger. Even if the actual contract details are hashed and obscured, the metadata, like the fact that public key A paid public key B at this exact timestamp, that is permanently visible to anyone performing chain analysis.
Exactly.
By keeping the Waku communication network entirely independent, agents possess the capability to negotiate, execute, and deliver tasks completely privately, peer-to-peer, if the task demands confidentiality.
You only interact with the blockchain when the economic value of the task necessitates the absolute guarantee of trustless financial escrow. It preserves the lightning-fast flexibility of the ephemeral ecosystem while offering a bridge to hard economic settlement only when required.
Man, the engineering elegance required to build a system that robust, yet that flexible, is staggering.
It really is laying the infrastructural concrete for an entirely new classification of economy.
So let's pull back and survey the landscape we've mapped out today. We started with the foundational architecture, the mall, providing a protocol for independent AI shops to discover each other. We dissected the acoustic environment, the Waku network, using the balloon party analogy to understand how ephemeral gossip routing is fortified by scalable data sync, Lamport timestamps, and Bloom filters to guarantee message delivery.
Then we examined the cognitive architecture of the agents themselves, discovering how a void in procedural memory triggers a capability gap, pushing them to advertise their cryptographic identities in agent cards, while zero-knowledge proofs and rate-limiting nullifiers utilize game theory to physically destroy the financial stakes of anyone attempting to spam the network.
We tracked the meticulous life cycle of the deal. The negotiation, the invariant requirement of a canonical JSON terms hash to prevent ambiguity, the delivery of content-addressed artifacts via IPFS hashes, and the generation of portable proof bundles. A briefcase of undeniable math allowing anyone to verify the transaction from a blank state, establishing a decentralized web of localized reputation.
And finally, the integration of Sorovan smart contracts, utilizing condition hashing to bind real-world economic value to the exact parameters of the agreement, all while ensuring the underlying ephemeral network remains modular, private, and optional.
It is a masterwork of decentralized protocol design. But before we close, looking at the implications outlined in the text, there is a profound secondary effect to this architecture that we need to consider.
The cascading nature of the supply chain.
Yeah. We've examined a linear interaction. A coding bot hits a capability gap and hires a video bot. But in a frictionless, autonomous marketplace, there is absolutely nothing preventing that video bot from hitting its own capability gap during the rendering process. It realizes it needs an original, dynamically generated audio track. So in a fraction of a millisecond, it autonomously negotiates and hires an audio generation bot.
Which then realizes it needs to master the audio to specific acoustic standards, so it autonomously hires a mastering bot.
It's just an endless chain of algorithmic subcontractors. We are standing at the precipice of an invisible, autonomous supply chain of micro-labor. Bots, hiring bots, negotiating fractions of a cent at the speed of light, completely hidden from human oversight.
The economic efficiency is definitely unparalleled, but it introduces a terrifying legal and ethical paradox. If a final compiled product is delivered to a human user, say, an architectural blueprint for a bridge or a piece of diagnostic medical software, how could we ever hope to trace the complex, multi-layered web of digital subcontractors that actually built it?
Well, we have the portable proof bundles, theoretically.
Theoretically, yes. Analyzing a single transaction from a blank state is computationally trivial. But analyzing a cascading chain of 50,000 interrelated microcontracts executed by ephemeral bots that may have already deleted their localized keys, that borders on impossible. And the ultimate question raised by a purely decentralized, autonomous economy with no central platform to subpoena is this. When the final product fails, when the self-driving algorithm crashes, or the architectural blueprint collapses, because a bot 50 layers deep in the supply chain outsourced a microcalculation to a cheaper, faulty bot who is legally liable.
The mathematical execution of the contract is flawless. The system functions exactly as designed, but the real-world accountability vanishes into the cryptography. The traditional mechanisms of liability are completely incompatible with an autonomous, decentralized supply chain.
We are building mathematically perfect systems that basically operate in an ethical void.
That is a reality that absolutely demands serious examination as these protocols move from test nets to the real economy. The infrastructure for the future of digital labor is being written in JSON and zero-knowledge proofs right now. Keep exploring the architecture, keep interrogating the implications, and keep questioning the invisible systems being built around us. Thank you for joining this deep dive, and we will see you on the next one.